Okay. All righty. Okay. Great. Okay. All right, we left off at marbling, at least my marbling, I don't know what to do. But we left off at discussing, understanding the structure of graphitizable and non-graphitizable carbon. And our understanding of these structures, have been established for a while, given the pioneering work of Rosalind Franklin, who solved the structure of non-graphitizing carbon via X-ray diffraction, which was a huge feat in 1951. So we talked about the difference. We started to talk about the differences between graphite and hard carbon, the historical terms for hard carbon, and why it's called hard carbon because of mechanical properties. And you sort of already have a feeling of that given the macroscopic observables, which is, you can easily write with graphite, it's softer than that of carbon. Now, in review of our discussions all the way back to the first lecture, where we talked about differences in how to design materials, particularly lithium-ion battery anodes, we talked about generally how sodium ions are larger than that of lithium ions and thus tend to exfoliate graphite when they're used as the anodes for sodium-ion batteries, and thus we turn to other materials such as hard carbon, right? So in reviewing those differences, here we see a schematic of graphite where it's the layered structure as one would expect. In terms of how ions fill these materials during charge storage, the mechanisms are different because the structures are different. For the layered graphite material with van der Waals layer despacing of 3.3 angstrom, we see that they're mostly intercalating ions because that's the mechanism of charge storage. But with hard carbon, there are different crystallite sizes where you have areas in which there is some nanodomains of what is graphitic or graphite-like, but mostly you see here more disordered structure in hard carbon with expanded interlayer spacing in the nanodomains of regions that one could classify as graphitic-like. Okay. And so the mechanisms of which these ions can be stored in hard carbon are denoted and summarized here, where you could have intercalation. So that's the black dots that you see here. So you could have intercalation in between the layers within these nanodomains. You could also have these voids, so these pores, and ions can fill in those voids as well. So those are pore filling. You can also have surface adsorbing ions. So here you see in the yellow circles, they're not intercalated in, but they're right on the outside of the nanodomains, and they're adsorb or chemisorb, as you'll see the terminology used in various papers. And then there's also these defect binding sites. And that's sort of a catch-all for, maybe the size domain is not exactly, graphitic, it's in between, it's basically disordered. And there could also be atoms that attract sodium ions. And so it's sort of a catch-all for, just some sort of defect either within the structure or because of the presence of a heteroatom that draws the sodium ions there. And the description of all these types of storage mechanisms tell you what the dependence is in terms of how to drive ions there, right? So the pore size makes a difference. So the surface area of the overall hard carbon anode makes a difference as to how many ions you can store, and thus affects the specific capacity. So it's always a trade-off, because if you have higher surface area, you could have more pore filling ions. So presumably you can increase your capacity, but you now have to pack way more material into your anode, right? Your tap density is much lower because you have high surface area, you have such a porous structure. Right. So it's a trade-off in terms of how much material you need to load into your anode from an engineering perspective, and then from a chemistry perspective or surface engineering perspective, it's a trade-off. So that is the reality of using a hard carbon. In terms of methodologies for engineering, should you increase the surface area? Should you, create pore sizes that are larger to, depending on what voltages you're trying to achieve? But that depends on which school of thought you subscribe to when it comes to the actual charge storage mechanism of hard carbon. So here, the two schools of thought are, if you could have potentially, when you cycle this material, you see the voltage versus specific capacity. And this is voltage versus sodium plus. And so you see some stark differences between the voltage profiles, which tells you that there's going to be differences in the crystal structure as we know, the thermodynamics as we know, the kinetics as we know. So everything's all intertwined. And one school of thought, which was the original school of thought back, when Jeff Don was studying these, and even before Jeff Don actually, several folks have studied over the years, but it could be subscribed that the sloping region is more that of intercalation. And we've seen that, right? We've seen the sloping voltage curves as indicative of like a solid solution intercalation mechanism. And then there's this plateau section, which can be attributed to adsorption mechanisms. Now, why do you care about which region it is, right? Or the flip, which is adsorption occurs first and then intercalation. Now, why should you care? You care because it affects how you engineer and synthesize the material. Right? If you think this is intercalation, right? And you want to drive down, the voltage, and you want to go to as low voltage as possible to expand the electrochemical window, increase your power density. If you want that, then you kind of have to limit and say, okay, if I want intercalation to increase, then presumably you want your d-spacing to be larger so that it can, facilitate fast ion kinetics. Right? So then that presumes your, nanodomains of these little graphene sheets stuck together here and there, you should increase that if it's more intercalation. Now, if it's more, let's say, and then continuing on, there's adsorption. Now, that also affects, let's say, your d-spacing layer, how you basically burn or pyrolyze the material under different gas environments. That affects your d-spacing. So it tells you, should I increase my pyrolysis temperature so that my d-spacing increases, so that I increase the intercalation mechanism? D-spacing decreases. So should I limit my pyrolysis temperature? Right. Or if you think, okay, well, I want to basically try to just maximize this specific capacity as much as possible, in which case I should increase my surface area, in which case then I basically keep on increasing the pore volume for sodium ion intercalation. So depending on which school of thought you subscribe to, and there's evidence for both, it does affect how you engineer your material. Okay, and the second school of thought, the new, relatively new, as in like within the last decade or so, that's based off of X-ray scattering and high resolution Raman, that tells us more about the structure of the material. So it's actually still up for debate as to what mechanism is actually going on. So I won't conclude one for you is what I'm saying. Now, so that's just the crystal structure itself. I mentioned add atoms. And there's been quite a bit of electrochemistry, electrocatalysis, I should say, that's been done to sort of promote the adsorption of sodium ions. And there is a plethora of add atoms that one could add to the material, to just the carbon itself, to promote basically the creation of defect sites so that there's more storage, or and also facilitate the kinetics of the storage. And some of the other strategies for manipulating the despacing due to pyrolysis or pore filling. So basically, you can increase surface area by a number of ways. You can supercritical CO2 dry it. So you pump in supercritical CO2. You can really expand the surface area of the material. You can pyrolyze under different gas conditions. You can start off with different carbonaceous precursors to really get different pore sizes. So there's a lot of ways to basically manipulate all of these strategies. And then also, of course, there's also electrolyte decomposition, which can really tweak the chemistry of a sodium ion liquid electrolytes to basically prevent irreversible sodium ion trapping within the carbon structure. Now, interestingly, this has not really been seen, or that's not true. The use of biomass precursors have really been explored for sodium ion battery anodes for hard carbon production, has really ventured into basically the use of materials that one could find in conventional agricultural products, like using byproducts like these almond shells and what have you, or walnut shells or scrap wood, basically things that you can pyrolyze that will then produce carbon at the end of the day. And that's what you see here, some processing where you can ball mill and then sort through different sizes. You can wash basically with acid and then basically just dry under argon and nitrogen for in a stepwise fashion for several hours, and then you get these carbon products. Now, one of the reasons why this is because you end up with this is desired because you end up with a highly defective material, which is great. That's what you want in hard carbon versus synthetic graphite, where you really have to control the environment, the conditions, so that you get these beautiful, clean, graphitic samples. But this not so much. You can etch out a number of organic residues with the acid and leave behind a disordered carbon structure. So there are advantages. Obviously, you use scrap materials, which is good in the sense of recyclability and even upcycling these products that normally maybe would go to waste, although in agriculture we have a pretty good tendency to compost a lot of these materials, so they probably would have been useful for other purposes anyway. But here's another repurposing of biomass materials, plant mass. And in terms of understanding the disorder within these materials, we turn to Raman spectroscopy. It's a heavily used, in addition to cylindrical X-ray scattering, it's a heavily used technique to really understand the ratios of how quote unquote ordered a carbon material is. And there are many modes, right? In terms of Raman spectroscopy, we discuss the modes as normal modes because these are solid structures where all the atoms move together. Unlike what you may have already discussed, when you were learning about FTIR and you're learning about modes of vibration and rotation in molecules. Those are independent molecules, whereas these are solid structures and all the atoms are moving together in these normal modes, right? So there is no such thing as isolated vibrations. They're all moving together, these atoms. And we can classify them as, symmetric normal modes, vibrational. They can also twist all together. But all these modes, we can classify them and try to understand the disorder in these carbon materials. And we also really want to have a quantitative, at least a first pass, first approximation understanding of how to quantify disorder. And in Raman spectroscopy, typically we try to measure this LA, this average lateral graphene size. So, you know, how big is that nanodomain of your graphene before it gets, you know, disordered and then packed in the different, you know, orientation. And the way we measure that is using Raman spectroscopy. And as a first pass, you can take the integrated intensity of the G band relative to that of the integrated intensity of the D band. And you multiply by this prefactor that's been worked out. So this is an empirical equation, right? That's been generalized for all wavelengths. So your spectrometer has different wavelengths that you can choose from in the visible region. And you can, you know, plug this in and you get a relationship. Now for 514, these are the bands that happen to show up at, you know, 1580 wave numbers. And then for the disordered D band, that's 1350. Now that's a first pass. You know, you just take the general integrated area using, let's say, fitted Lorentzian curve, but you can break it down even more so. And, you know, instead of just the D band here and just the G band here, you can really break down these modes into this D1, D2, D3, and all of them are tabulated like so. So D1, you know, the G band is the E2G mode, and so on and so forth. And the A1G is the D1 band mode. And so you could really tease out and try to understand the level of disorder with great specificity within your material. Now, most of the literature that's out there lies somewhere in between, you know, caring about the breakdown of these specific modes and sort of its general quantification of this is the general order of disorder in the material, and this is the, you know, the average crystallite size, and it gives you a trend. And for the most part, it's a good enough approximation to try to understand if I increase, you know, my graphene domain size and I'm increasing the circulation, is that increasing my capacity? And for the most part, you know, first order approximation is good enough unless you're really trying to probe, you know, very specific quantum modes and you care about, you know, phonon dispersions and graphene and all of that. But these materials are so highly disordered that lumping them all under like D versus G band is sufficient for, you know, making general conclusions about how you treat the material and how it performs electrochemically. And you can do that. You can track, you know, what happens to the disorder, what happens to the electrochemical performance with all of these, you know, heteroatoms. Because once you introduce these heteroatoms, they're going to affect the modes of all of in the carbon material. And so the popular ones in terms of heteroatoms to add are nitrogen. That's obvious. You can easily dry or pyrolyze carbonaceous precursors in a nitrogen atmosphere or even in an ammonia atmosphere. There's also sulfur doping. Phosphorus doping comes naturally if you're using biomass precursors, because that's typically in fertilizers already. Now, boron and fluoride doping are a little bit more, I would say, exotic, and they all have different reasons for why you would want to do that. You know, either you're trying to increase ion conductivity, you're trying to adsorb more sodium ions, or you're trying to prevent trapping because of kinetic promotion. And so it all goes back to the electrocatalysis of the role of these atoms for the carbonaceous materials. Now, of course, there are some downsides to using heteroatoms. While they, you know, can add, let's say, certain improved kinetics, there are some downsides to, you know, you can cause, like, let's say, for sulfur or fluoride or phosphorus doping, you can add and cause structural deformations that are unintended. And so while you improve kinetics and you have diffusion rates that are faster, and subsequent cycling, you introduce more disorder in the breakdown of the material by having these adducts. So once again, we go back to the general theme of battery design and battery materials engineering is that it's always an offset. There's always a balance in terms of adding things to a material to improve some electrochemical performance, but cyclability, might pay the price. So, but that is where we're at in terms of hard carbon design. There's still a lot to do, and particularly, the use of upcycling biomass and plant-based materials for hard carbon production. So I think it's pretty exciting because you can obviously just go out and just try to upcycle waste that might just go into the compost and design new hard carbon materials and increase basically improve the circular economy for these types of electrode materials. Okay, so with that, I am going to, oh, no. Yes. So the question is, why would you expect smoking for intercalation? Because for adsorption. So you subscribe then to the second school of thought, where you think intercalation should be flat. Well, so there is, so from like the works of from the 70s of Don and all those folks studying intercalation and staging, the sloping effect, you would expect then that the chemical potential is changing as you're increasing the amount of sodium, or I guess in their case, in graphite. So you would expect a change in the chemical potential that way, which then results in a change in the relative value in the relative profile. But this goes back to our understanding, or maybe not lack, there's a lot of structural characterization out there, but I think it goes back to our discussion of what is the structure that we actually have. right? And what is the mechanism of pore filling or ion storage that occurs first? Because I see the evidence of both. So it's difficult, but I think it goes back to possibly we might be missing, while the characterization has been done, I think the data that is there might not be accessing certain features that we're just missing because let's say there are maybe pore volume that is small, like micropore. So that's, what 2 nanometers small, that diameter pore. And those are not accessible at the beginning, but then they evolve and become accessible. So then your structure is sort of evolving and changing, but you didn't capture when you first just do the like execute characterization of the pristine material. So I think that's where the debate lies. It's not that I think people don't understand how to correlate the mechanism, the electrochemistry to of the mechanism, but I think the ambiguity and vagueness lies in the fact that we're not covering the whole structure, which I think throws off. So your comment, I think, would still be valid, but the fact that there's potential that we're not capturing filled pore volumes that become open later on, that kind of thing. I think that is where the debate lies. And there's evidence for both depending on what structure you go with. That's my very gentle assessment of the field without, starting a full on, without like really teasing out all of the details of, each paper and saying. But I see what you're talking about when it comes to the lithiation phase in the voltage profile. Well, yeah. I'm trying to succinctly describe the date, which is been going on for 10 years. But I would say maybe the new data. It has, yeah. Well, maybe it's more than 10 years. Maybe it's 15 years. What structure are we really missing? Anyway, okay. I'll tap my presentation of the evidence there. Difficult measurements. We continue on with the discussion of conversion battery materials and alloy battery materials. Also new and exciting, but comes with a lot of nuances. So we'll discuss what those nuances are. All right, so let's go back to our discussion of lithium sulfur. We briefly touched upon this when we were talking about the previous module in polysulfide shuttling suppression. So now we take a deeper dive into the methodologies and strategies for suppressing polysulfide suppression, because if we can get this to work, obviously lithium sulfur batteries and also magnesium sulfur, sodium sulfur, we've made the sustainability argument that there is a whole lot of sulfur byproducts from petroleum refining for us to use. There's an abundance of sulfur resources beyond petroleum refinery, and thus, the earth abundance and also the economics argument, make this type of system attractive. But the real issue is fundamental. We are trying to convert a sulfur cathode that has, this orthorhombic structure with, sulfur 8 rings that will have to be open. So it has to be a ring opening polymerization process, and then conversion to the final product of Li2S, which is this rock salt cubic structure that you see here. So you see already that this is quite different from the intercalation-based cathode materials that we talked about before, where we're trying to actually minimize lattice parameter dilation and contraction to maintain the pristine parent phase. But now there's going to be large volume changes. And so this is basically the main issue of conversion-based materials. You know, this is not just for lithium sulfur, but for all conversion-based materials, you will have to deal with large volume changes. Now, when we talk about alloy materials, we're also going to face the same issue. And so the general theme here is, how do you deal with large volume changes? And also, how do you deal with materials that are not as electrically conductive, like silicon? It's a semiconductor, but as we all know from photovoltaic work, right, that there's a lot of doping that goes on to so we're trying to solve these intrinsic problems in this material, and that's what the whole field is doing, is trying to suppress polysulfide suppression, improve kinetics, improve electroconductivity in the material, basically make it a quote unquote better electrode, to about the description. And this work has been around for a long time, sort of the theme here, as well as there's been a lot of work already done on these types of materials. But over the years, what we've gotten better at is either stabilizing the materials or making composites that have higher cyclability. But you can see here, you know, since 1962, people have already explored the use of sulfur as a cathode in lithium-ion battery type material. And then the evolution over the years, you're going to see a theme where, you know, for like almost a decade, actually a decade, basically a decade of just composite engineering. And you see here, how do you suppress the shuttling of these polysulfides, the lithium polysulfides that decrease your active material and also decrease the cyclability, because now you're transporting these side products over to the anode. Well, you can try to trap them all, and that chemically trap them, physically trap them, and that's what all this work here shows. You can put sulfur in carbon structures to basically limit the volume expansion. You can put it in these polyaniline type structures where there's a bit of a void, so that basically the expansion can occur in the void. But the material is a polymer, and so it's, you know, typically more lightweight than, let's say, metal additive. And that's what you see here. A lot of hollow structures, sphere design, inverse vulcanization was really popular 7 years ago, where basically you arrest the polysulfide shuttling by cross polymerization with this DIB, this diisopropanyl benzene polymer, and it's called inverse vulcanization because vulcanization is, of course, where you try to make sulfur bridges to then cross-link rubber, to make rubber, basically, by creating sulfur linkages. And so what you do with inverse vulcanization is you suppress that. So you open the S8 rings and then you cross-link it with polymer so that polysulfides are not generated, and then they're anchored by the polymer that's cross-linked down to the sulfur polymer, and thus does not get shuttled over to the anode. So there's a lot of work when it comes to inverse vulcanization. That's a very popular strategy. And of course, vulcanization is historic to the state of Ohio, right? Goodyear is from Ohio. And so this state has a rich history in understanding the chemical engineering of vulcanization of rubber materials. And that is why our tires work the way they do. That's why they don't fracture, is the way they do. So anyway, that's There's a long history in that. Additives like lithium nitrate help to suppress polysulfide shuttling as well. 1 weight percent in your electrolyte will improve the electrochemical cyclability dramatically. And so where are we now? We're now really getting down to not just polysulfide suppression engineering, but point specific, like atom specific and engineering, where we try to add in, add atoms, again, similar to that of hard carbon, to improve the kinetics of the battery, but also improve sulfur redox, because it's extremely sluggish, right? We talked, when we're talking about sustainability, we're talking about the cost of having too much electrolyte. We talked about how to design leaner lithium sulfur batteries so that you're not drenching your lithium sulfur batteries in electrolyte to get, to get basically the battery to work, to get the wettability of the cathode to increase to get the battery to work and improve the sluggish kinetics. The sulfur is electronically insulating, so you really have to, motivate the sulfur redox. Now, you can try to do that through electrocatalysis as well. So you basically add in a whole physical layer to both promote the kinetics and also trap the polysulfides. And that's what many people have tried to do. And you could also try to increase the electroconductivity by adding in these maximes, which of course you may have already all heard of, given that they became quite popular around 2007, 2009 for increasing electronic conductivity, but also pseudocapacitance of batteries. Supercapacitor, I meant to say. Anyway, there's a lot on maximes, but anyway, there's been a lot of engineering that's done to basically work on those 2 key factors. 1, suppress the polysulfide shuttling, and then 2, increase the kinetics of your of the sulfur redox chemistry. Okay, and then protect lithium as well, because if you're going to put against lithium anode, surely there needs to be some protection there so that you suppress filament growth. Okay, so in terms of going back to where it all started, in terms of encapsulating sulfur so that you start to suppress the polysulfide shuttling and also maintain the sulfur expansion. We looked at Lyndon Nazar's paper back in the day on putting sulfur into ordered mesocarbon. So similar to ordered silica supports like SPA15, there's ordered carbon supports CMK3. And so by basically just melting sulfur into these structures above its sulfur's melting point of 135, so you just have to be at, let's say, some gentle temperature of 155 degrees C, you can achieve high capacity. So here that's 1,000 milliamp hour per gram. That's about 75% of the theoretical capacity of 1,600 milliamp hour per gram. So that's pretty high. That's really high sulfur utilization there. And you can see this work has been cited quite frequently. These are only 2 examples of review papers. But what you often see is the overlay of these lithium polysulfides on this original figure. So if you look at this review paper, you see that the proposed polysulfides are, Li2S8, Li2S6, Li2S4. So these are soluble lithium polysulfides in the ethers. That means they're going to dissolve and then get shuttled back and forth. And then you also see the proposed production of Li2S2 and Li2S. Now these are not as soluble. So where are they going to end up? They'll end up typically either on the anode and then form, an SEI that's not desirable, or they come back and deposit back on the cathode side. Also not desirable because now you have inactive, electrochemically inactive Li2S. That's not going to contribute to capacity. That's not going to contribute to cyclability. You're losing active material. And so all deleterious reactions, basically. And then you see another review paper where you see the ring opening polymerization to form the same polysulfides. Although I have to say, in the original paper, they didn't actually propose that, as you can see here. Okay, so is the mechanism that you're really producing the longer chains lithium polysulfides and then producing Li2S. Now, there's evidence to suggest that you could potentially form Li2S basically on the first slope into the first plateau. So why would that affect your engineering of this cathode? Well, if you thought you weren't going to produce Li2S until lower voltages, and you could just reduce your voltage window so that you form these longer lithium polysulfide chains so that they're dissolvable, and you can maybe trap them in some way, versus just having Li2S fall out and deposit on the cathode or something like that. That affects how you engineer your catholyte. Okay, so because if you think, okay, well, I make these long chain lithium polysulfide, so maybe I can change the solvent in some way, so that the lithium polysulfides are not as dissolvable and they get transported. Then that's one strategy. But if you're also now forming Li2S at the beginning, then you have to deal with, okay, how do I trap and make the catholyte perform in some way where I'm not producing Li2S like immediately and using sulfur active material immediately. That changes your engineering strategy from just electrolyte engineering to now potentially composite engineering as well. Okay, so it does matter how you understand what materials are produced, and that's been a huge effort. That's been why people have tried to study the polysulfide and lithium polysulfide production in situ. So here's a fantastically detailed Raman spectroscopy paper out of UIUC, and this was done in situ in a Raman in a electrochemical cell where you can probe with a window. It's a custom-made cell where you can actually see the polysulfide being produced. And what you see is at various voltages, you start at open circuit potential of 3.2, which is actually relatively high. It's typically 2.8, 2.6, 2.4 volts versus lithium, honestly. But let's say you start off with this 3.2 open circuit potential, and then as you lithiate, right, all these species are being formed that you can detect. So there is a detection of, so here's the zoom in, here's the zoom in version of the right side. But what you see is the production of not only polysulfides, but you also see sulfates that are being formed. So now your pH is starting to change. And also you see this S3 radical minus, which in ether base is this iridescent, like beautiful aquamarine blue color. So you can, what that means now, you can also probe using like UV-Vis type techniques to really detect all these species that are occurring. Okay. So not just the S4 minus that you would expect, but also S4 minus, S3 radical minus, and all of that. So what that tells you is, okay, well, you have to now deal with all these species. That's what your electrolyte chemistry design is going to have to do. And so that really affects where we end up in terms of, the eventual battery design, right? Because your electrolyte now has to work in a way where it suppresses the dissolution of these polysulfides and thus the shuttling of the polysulfide. So if you want to have high mass loading, like 10 milligrams per centimeter squared, which is extremely high. I mean, if you can get like 5 and cycle that like 1,000 times, that's pretty high already. But let's say you want to, state of the art, you want to put this in a pouch and eventually put it on some electric vehicle, you have to be aiming at very high sulfur mass loading, which means now your electrolyte has to deal with the dissolution of the polysulfides, but you also have to design it in a way where you have to increase the sluggish kinetics of sulfur. And when you have more and more sulfur, right, do you increase more and more electrolyte? Do you increase the salt concentration, in which case the viscosity, it becomes very thick, and then, ion conductivity is going to decrease. So it's really a balance of how do you get more active material, higher energy density into your electrode, but prevent all of these side reactions from happening, right? And also have a lean operation of less than 3 microliters per milligram of sulfur. I mean, that's extremely dry, extremely low, right? So that is where we are in terms of sulfur design, is how do we basically keep the structural integrity of the electrode while increasing the kinetics, basically through electrolyte design or physical barrier design, so that you can trap and stop the side reactions, but basically not add that much more weight. And that's what we've seen with the cost analysis of the sustainability design is, once you start increasing or once you start introducing, let's say, a lithium protection layer, like a solid electrolyte to suppress lithium filament growth in lithium sulfur batteries, you're increasing the costs, and so where will you end up with parity and competitiveness with lithium ion batteries, with lithium metal anodes, or even graphite anodes? Well, that comes down to, the cost analysis and how thick your material is, but that's where we are. So in terms of trying, it's like decades worth of numbers. So it's a little bit difficult to summarize all of them. And you can see it's quite heterogeneous, right? It's all over the place in terms of standardization. So all these numbers, you could see, there's comparison. You can achieve really high initial capacity, but then this is at 10, C over, 0.01 C. So C over 100, right? I mean, that's extremely low. Basically, you're just allowing thermodynamics to flop along, right? So this is not electrochemicals. This is not the typical out of equilibrium that you're expecting from a battery. There's attempts at, going to higher C, but this is C over 20, here's C over 10, here's C over 2. So that's kind of interesting, but you can see the comparison is sort of all over the place. And so I show you this to say, not just for lithium sulfur batteries, but for all battery materials design, you really need to pick a lane and compare apples to apples, right? So if you're working on anode design, or you're working on cathode design or electrolyte design, you can always pick a system that will, or conditions where your material will perform the best in comparison. You can always pick a bad battery to compare against, but that's not really fair. So in terms of apples to apples, you really want to pick something in the literature that has as close to the conditions that you have as possible. Now, if you're working with a new material, then obviously, there wouldn't be a similar material that you're working on. If you're working on composite, probably there's something in the a material, one component that has already been reported on, you should pick that. But what really needs to happen is standardization of electrochemical testing, so that we can really say, if I have the same mass loading, I have the same concentration of additives, I have the same electrolyte, I have the same thickness of electrode, I have the same cycling rate as normalized by the theoretical capacity or something like that, then you could say, I see an increase in X, then it's believable. And it's not, well, I picked, the worst battery, and now my performance is like 10X. That's not really fair. Okay. Now this is not just for battery testing. This is, the electrocatalysis community has been going through this. You can always pick a fuel cell that performs worse than your fuel cell to publish a paper and say, oh, I did something better, right? Without really understanding the mechanism. So standardization, try to pick something, for your work plan. This is now more for those that are turning in their work plan, but for your work plan, try to pick the best case, state of the art, under the same conditions as best as you can, so that you can really say, you know, I anticipate an improvement in this quantity, you know, so and so. Okay, so anyway, okay, so more examples. Okay, what hasn't been tried is probably the better question to ask than what has been tried. Now, there's a lot of work with polyaniline and polyacrylic nitrile because they're lightweight materials, they're conductive, and thus the conductive polymers. So you increase the electronic conductivity of sulfur, which is great. Plus, you're adding in a polymer, which will help plasticize and, you know, make your electrode more cohesive. And so overall, the mechanical properties are improved. And so a lot of people have looked into this. And of course, carbon nanotubes as well has been looked at, you know, for doing the same thing, increasing the electronic conductivity. And so that's what you see here. I mean, you see everything under the sun, you know, in terms of what composites are have been added, and, you know, the different capacities that can be achieved. Although interestingly here, this one reported for the initial capacity, basically theoretical capacity. So yeah, which is difficult. So one has to look at the normalization as well. You know, if you have very little sulfur mass loading, you can always try, you can basically get as close to theoretical capacity as possible by decreasing the sulfur content, right? So is it 10% of your electrode, or is it 50% or 70%? I mean, 70% would be, you know, more ideal, but this data table doesn't actually tell you that. You really have to dig and see, you know, is it a sprinkling of sulfur in the electrode, or is it something realistic? Okay. Okay. There's more. I'm not going to belabor the point. Oh, yes.
So are these capacity for the sulfur mass, not the total, like after the metal mass?
Yes. And very emphatic, yes. And that is because what you'll see is if you have a lot of carbons, then you can really improve the kinetics, right, by increasing the conductivity. But what's going to happen in the long run is then the SEI on the carbon is also going to contribute to some deleterious side reaction. So that's something to take into account. And that's, I would say that's been sort of what has plagued some of the lithium sulfur work, is that you see these fantastically high initial capacities and maybe even cycling rates, but then you realize the amount of sulfur content is like less than 50%. So then is your electrode really a sulfur electrode, or is it carbon with a sprinkling of sulfur? So yes. Correct. And this is going to be the issue when you try to translate from coin cell design to pouch cell design, right? And so that goes back to one of the earlier questions of